Hello everybody, welcome to E-Pathshala once again. I am Tapabrata Sarkar from the Department of Earth Sciences, Indian Institute of Science Education and Research, Kolkata. So today I am here once again to lecture or deliver the second part of the module or the talk on the decay schemes of potassium argon, rubidium strontium, uranium lead, samarium neodymium isotopic systems, its petrogenetic implications and its uses in the radiometric dating of minerals and rocks. As I have said in the previous lecture, this module will be converted or will be covered in two lectures. I delivered the first lecture where I actually covered the different types of isotopes, where I described that there are two types of isotopes. One is stable, which remains indefinitely in the same way, and the other is radioactive, which decays with time into some stable nuclides. And this decay of the radioactive isotopes is proportional to the number of parent atoms present in the sample, and which is this proportionality constant is called the decay constant. Then I discussed about the decay of the radioactive parent to the stable daughter, and so that it depends at any time, it depends on the number of parent radioactive atoms present at any time in the sample. Then I moved on to the concepts of half-life, where I discussed what is half-life, that the time after which one half of the parent radiogenic or radioactive isotopes decays to completely decays out to form daughter isotopes. And after that I moved on to build or derive the basic equation which is required for radioactive dating, and we use this basic equation to derive the specific equations of each isotopic systems, namely the potassium argon system, the rubidium strontium system, the uranium lead system and the samarium lead system. And we also discussed how from these equations the age and the term T or the age of the rocks and the minerals can be derived. So, this was the first part of the lecture, and now basically I move into the second part of the lecture, where I will mainly concentrate on the petrogenetic implications of these isotopic systems. Again, I will mainly concentrate on the petrogenetic implications of potassium argon and samarium neodymium system, and then I will use these systems, or to be more specific, I will use these systems to find out the ages or calculate the ages of different minerals or rocks. First is the hold rock, how to calculate the age of a hold rock using these isotopic systems, potassium argon, rubidium strontium, samarium neodymium and uranium lead, and then again using these systems for dating specific minerals. So, to understand these concepts what I just talked about, we need to understand two different things. One is two different concepts. One is the concept of blocking temperature, and the other is the concept of geological ages. So, this I will go into detail in the next part. So, first I would move on to the petrogenetic implications of the isotopic systems, and to understand the petrogenetic implications we need to understand some basic characteristics of the isotopic systems. For isotopes of heavy elements, the ratios in the magmas are characteristics of their source, and these isotopes of these heavy elements are not fractionated during the our characteristics of the source are not fractionated during any crystal liquid equilibrium. And why is it so? Why is it not fractionated? Because the difference of mass between the isotopes of the heavier elements are too small, and these cannot be differentiated during any processes of geological importance. So, this observation has significant petrogenetic implications. What are these petrogenetic implications? Is that the ratios of the isotopes of these isotopic systems discussed before are indicative of their source, and also we can find out any mixing or any interaction between different distinct sources. So, one important thing which these isotopic or these atoms or elements have in difference is their incompatibility. So, this incompatibility difference defines how they will behave when a geological process, for example, melting is happening. So, the incompatibility difference between the elements or the atoms what we are discussing now, among them rubidium has the is the most incompatible element. It is followed by thorium, uranium, lead, neodymium, and at last strontium and samarium. This means that rubidium being the most incompatible element will always try to move into the melt, and samarium and strontium being the most compatible will try to remain in the solid phase. So, these characteristic difference between the elements will define how the elements will behave in terms of crystal liquid equilibria. So, now to understand the petrogenetic implications of the isotopic systems better, we look specifically into the rubidium strontium system, and we need to see how the strontium isotopes have evolved through time. So, we can easily calculate the 87/86 strontium ratio of the bulk earth during the formation of the earth, which is around 4.6 billion years ago, from that of the chondriatic meteorite, which is considered to be the composition of the bulk earth or the bulk unfractionated earth. This can be calculated, and this plots more or less out here. So, from that time onwards, 87 rubidium has been constantly decaying to 87 strontium, and therefore, with time the 87/86 strontium ratio has been constantly increasing, what you can see along this line. So, it should have continued along this dotted line till the present day, but as you can see, this is not the case. This is because we have assumed, or it has been assumed, that around 3 billion years there has been a large scale melting event which produced some granitic type melt, and which has moved up to the surface and finally formed the continental crust. Now, as I have already said that rubidium is much more incompatible than strontium, the rubidium has concentrated in the granitic melt and ultimately in the crust. Now, if all the or most of the rubidium has concentrated in the crust relative to the bulk composition of the earth, then the more 87 strontium has been produced from that time on, and as you can see that the 87/86 strontium ratio has evolved with a much steeper slope from this large scale melting event. And what has happened to the mantle? It is just the opposite. Though after this large scale melting event, when rubidium has moved or preferentially moved into the crust, the rubidium in the mantle has been depleted. So, what you can see out here is that the strontium 87/86 strontium ratio has evolved with a much shallower slope than that of the bulk earth, which should have been the evolution path if no granite producing or large scale melting event had taken place at around 3 billion years. So, this is how the strontium isotope has evolved with time. So, what is basically the petrogenetic implication of such a diagram is that now if we collect any rock from the nature and measure the 87/86 strontium ratio, these ratios can give us an indication about the source of the rock, whether it is crust or whether it is mantle or it is a mixture of both crust and mantle. Now, if we look the same thing of the samarium neodymium system, the samarium neodymium system has behaved in a similar way, but kind of opposite to the rubidium strontium system. Why is it so? Because the neodymium is more incompatible than samarium. What we have seen in the rubidium strontium system previously is that the parent, which is rubidium, was more incompatible than the daughter, but here we see an opposite case where the daughter is more incompatible than the parent. So, in the similar way we can calculate the 143 by 144 neodymium ratio of the bulk earth when the earth was formed, that is around 4.6 billion years from the chondritic meteorite. And from this bulk earth 147 samarium has been constantly decaying to form 143 neodymium, and the 143 by 144 neodymium has been constantly increasing thereafter. But again it should have followed this dotted line till the present day, but this is not the case. Now, if we again consider a large scale melting event around 3 billion years, which has created a granitic type of melts and ultimately the continental crust, then most of the neodymium has been preferentially moved into the melt and ultimately deposited in the crust. So, the crust became depleted in samarium, while the mantle preferentially became enriched in samarium relative to the bulk earth composition. So, what we see is that here opposite of the rubidium strontium system is that the mantle has evolved, or the neodymium ratio of the mantle has evolved with a much steeper slope than that of the bulk earth, while the crust has developed, crust of the enriched mantle has evolved with a much shallower slope than that of the bulk earth. So, again what is the petrogenetic importance is that if we collect a rock from the nature and we measure the 143 by 144 neodymium ratio, we can easily find out what would be the source of the rock, whether it is crust or mantle or it is a combination of both. Now, also to understand the isotopic differences between the crust and the mantle, we have developed, or a term has been established which is called epsilon, and it is used to express the degree of the neodymium enrichment as the differences between the neodymium isotope ratios, for example, in the crust in the mantle are very small. So, epsilon Nd is been given or is equal to 143 Nd by 144 Nd 0, which is the initial 143 by 144 Nd during the start of the decaying process, divided by 143 by 144 Nd at time t of Chur, which I am going to say what it is, minus 1 into 10 to the power 4. Here 143 by 144 Nd at t of Chur is basically the 143 by 144 Nd ratio of chondrite uniform reservoir, which is actually called the CHUR or Chur, at time t of the formation of the rock, that is when the rock had formed and the decaying process of samarium to neodymium has just started. So, this is an equation term epsilon Nd, which has been developed to understand the enrichment of neodymium isotopes with respect to a fixed value, which is that of the chondrite uniform reservoir. So, as you can easily see from the equation that when we have a positive epsilon Nd, which meaning that the 143 by 144 Nd initial is more, which means higher 143 Nd, it means that the rock or the sample is derived from a depleted mantle source, because what we have seen in the previous slide is that we have 143 Nd higher than the bulk earth or the chondrite uniform reservoir in a depleted mantle source. Similarly, we can see out here when we have a negative epsilon Nd, that is we have a lower 143 Nd value, it comes from an enriched mantle or a crustal source, because 143 Nd is relatively depleted in the crust relative to the bulk earth, which is the chondrite uniform reservoir. Similarly, we can have a similar equation for the strontium system as well. The degree of strontium enrichment also can be expressed in the terms of epsilon Sr, which is again the 87 by 86 strontium initial, that is at the time of the formation of the rock or this time of the start of the decay process, divided by the 87 by 86 strontium at time t of Joule on the chondrite uniform reservoir minus 1 into 10 to the power 4. Here is the same thing, 87 by 86 strontium ratio at time t of Joule is basically of the chondrite uniform reservoir at the time of the formation of the rock, that is when the decay process has started. But what you see out here, when we have a positive epsilon Sr, meaning that we have a higher 87 higher strontium 87, it comes from an enriched mantle source or the crustal source, because as we have seen in the previous diagrams that 87 strontium has been enriched in the crust relative to the bulk earth, rather relative to the bulk earth, and we have a negative epsilon strontium value, that is lower 87 strontium. In if we have this value, then it comes from a depleted mantle source, because we have seen previously that 87 strontium is relatively depleted with respect to bulk earth in the mantle. So, what you see is the process is very similar, but this the values and the implications of the values are just opposite to that of the samarium neodymium system. So, one is neodymium is enriched in the mantle, but strontium is poor in the mantle, and the vice versa. So, based on this concept, what we have just developed about the epsilon neodymium and the epsilon strontium, we can develop a diagram where we have the epsilon strontium on the x axis, while epsilon neodymium on the y axis, and the different sources of the rock has been plotted in the diagram. I try to make it simple. If we have, when we see depleted mantle, we have positive epsilon Nd and negative epsilon strontium. So, that is what we discussed in the last slide. So, basically depleted mantle is plotted on this quadrant where we have negative strontium, negative epsilon strontium and positive epsilon Nd. While the upper continental crust, which is more enriched in strontium and depleted in neodymium, its plots in this quadrant where we have negative epsilon Nd while positive epsilon strontium. So, from this diagram, any mixing between these two distinct sources can also be easily found out. So, this is basically the petrogenetic implication of the combined two systems, rubidium strontium and samarium neodymium, that from the ratios of the neodymium and the strontium isotopes, we can easily or very distinctly find the source of the rocks and any melting process or any mixing process which have occurred in between these distinct sources. So, next I would like to move on to the radiometric dating of the whole rocks and minerals. This I have discussed in the previous section as well when we developed the specific equations required for radiometric dating for each isotopic systems, for example, the rubidium strontium and the samarium neodymium system. So, we have seen out there is that we can calculate or conveniently calculate the value of T, which is the age of the rock, if we know the different ratios which can be measured directly from the sample or can be found out from graphical analysis. But it is a common thing, we have noticed it commonly, that the ages found from different isotopic systems on different minerals yield discordant results. So, this is nothing wrong, there is nothing wrong in the process, but this is how it is. So, to understand why these results are discordant, we need to look more closely or understand more closely each of these isotopic systems and understand the meaning what these temperature or the term T or the ages actually mean. So, for this, two important concepts need to be understood. One is that of the blocking temperature and another is the geological age, concept of geological age. So, what is actually meant by the blocking temperature? It is the temperature at which a system is close to any isotopic exchange with the surrounding. So, this is the temperature at the radiogenic clock is actually switched on. So, when we get an age from these equations what we have developed, we actually get the age from when the mineral or the rock has crossed this blocking temperature. And next we move on to the geological ages. That there are different kinds of geological ages, and the most important what we normally deal with are the crystallization age, which is the age at which a mineral has crystallized. For example, a mineral has crystallized from a magma or a new mineral has formed in a metamorphic rock. And then we have a metamorphic age as well, which is basically the age of peak metamorphism, and another commonly used age is the age of crust formation age. This is the age when a new crust has formed from an older crust. Okay, so, what we see in this diagram is the blocking temperature versus the age which has been done from a study from Scotland. But what is more important is that what we see, the blocking temperature is very different for different systems in different minerals. For example, if we consider the uranium lead system in zircon, this has a different blocking temperature, the highest blocking temperature, and it is different from the same system of a different mineral. We see the same out here as well for potassium argon system. When we consider different minerals, the blocking temperatures are very different. So, what is very important from this diagram is that we need a very thorough knowledge of the isotopic systems and the blocking temperatures to correctly interpret the calculated ages. So, what we can see out here is that the age of these different minerals of the same rock is very different. Now, none of these ages are incorrect, but if we do not know the concept of the blocking temperature, and we will not be able to correctly interpret these different ages. Now, if we know this, we can get additional information. For example, we can join these points and find out the cooling curve of the rock, which means that how the rock has cooled with ages. So, next we move specifically to the whole rock ages. What do we mean by whole rock ages is that the whole rock ages are obtained from the bulk composition of the rock and not of the single minerals. The rubidium strontium and the samarium neodymium systems are the most commonly used for determining whole rock ages. I will just briefly start with the rubidium strontium system. As we have discussed in the previous lecture, we derived this equation that 87 strontium by 86 strontium equals 87 by 86 strontium initial plus 87 rubidium by 87 strontium into e to the power lambda t minus 1, and this equation is in the form of a straight line in the form of y equals c plus mx. The ratios 87 by 86 strontium and 87 rubidium by 86 strontium can be directly measured from the sample using a mass spectrometer, and the initial ratio of 87 by 86 strontium in the rock during the time of the formation can be obtained using the isochrone method, which I discussed in detail in the previous lecture. So, as lambda is a constant, we can easily calculate the term t, which is actually the age, the time which has elapsed from when the decay process of the radioactive element, that is the rubidium, has started. So, what are the advantages and disadvantages of the rubidium strontium system in dating or in finding the whole rock ages. The advantages are that the rubidium and strontium are abundant in crustal rocks, and the concentrations, or there is a large variation in concentration of rubidium and strontium. And the most important disadvantages of the system in measuring the whole rock ages is that rubidium and strontium are relatively both mobile elements. So, they tend to get lost, or the isotopic ratios are disrupted with the influx of fluid or later thermal events. So, we need to be very careful with the ages that has been obtained from this rubidium strontium system. So, the samarium neodymium system whole rock ages is also very similar to that of the rubidium strontium system. The system works very similarly. We can the equations what we developed for the samarium neodymium system in the first lecture, from there we can easily calculate the age of the rock. Some of the ratios we can directly measure from the sample using a mass spectrometer, while the initial neodymium ratio can be obtained from the graphical method. What are the advantages and disadvantages of the samarium neodymium system? Is that both samarium and neodymium are relatively immobile. So, they are not much affected by this fluid or later thermal events. But what are the disadvantages is that samarium neodymium are in very low concentrations in the crustal rocks, and for this system the half life is very long, which means that the samarium neodymium system has a very long half life, which means that it takes a very long time for samarium to decay into neodymium, which means that the concentration difference of samarium and neodymium is pretty low. So, this system is applied or is useful only for very old rocks where the concentrations are enough. The next I move on to the dating of single minerals, which is a little bit different from the dating of the whole rocks. When we date the whole rocks, we take the bulk composition of the rock, but here we find out the concentrations of these isotopic systems or these isotopic ratios from a single mineral. For example, for rubidium strontium system, we try to find minerals which are concentrated or which has a relatively larger concentrations of rubidium as well as strontium. So, rubidium behaves very similarly to potassium. So, rubidium is concentrated mostly in potassium bearing minerals, for example, muscovite, biotite, and to some extent in K feldspar. So, we to measure the ages, we can easily measure the ages of these minerals using the rubidium strontium system. But again, the most important disadvantage is that rubidium is a very mobile element. So, the ratios, isotopic ratios can be easily disrupted with some movement of the fluids as well as some later thermal events. For the samarium neodymium system, it is the technique is very similar to that of the whole rock ages. We need to find the concentrations of the isotopic ratios in minerals where it is most concentrated. So, samarium is generally concentrated in the mineral garnet. So, we can use this mineral as to date this mineral using the samarium neodymium system. But the disadvantage is that you need to find a rock with the mineral assemblage or the mineral garnet should be present in that rock, and the mineral should be relatively old to have enough concentration of neodymium, which has formed from samarium. So, I now discuss the last isotopic system, which is extensively used for dating single minerals, that is the uranium lead system. It is extensively and most effectively applied to minerals like zircon and monazite, but it is also applicable to other minerals like sphene, badialite and perovskite. So, the ages of the uranium lead system can be obtained independently from two separate isotopic systems. As we have seen before as well, the concordant edges should lie on a Concordia curve, which I also described in detail in the last lecture, and the discordant points also lie on a straight line which is called discordia, with an upper and lower intercept on the discordia, which also has specific geological system, which has been also discussed in the last lecture. Now, I just come a small example of the uranium late dating of zircon, which is a very robust geochronometer. Why is it so? It has been the uranium lead system, as I said, is extensively applied on zircon, because it has a very high closure temperature of greater than 1000 degrees centigrade for especially the uranium lead system. Moreover, the mineral zircon prevents loss of any lead by diffusion after it has crystallized. So, there is no loss of lead. So, the edges remain intact for a very long time, and the mineral is also mechanically and chemically very durable. So, it can withstand weathering and erosion, and it can record multiple edges from a single grain. And also another important factor is that with the development of the new imaging and analysis techniques, we can record multiple edges from the single grains. As you can see in this figure, the shape and size and the texture of the grains are very different, and we can analyze these different spots and we can get different edges which have very specific geological significance. For example, you can see the different in edges in this core region and in this rim region, and also the shape and the textural differences between these three grains. Before I conclude this lecture, I would like to summarize what I have already discussed so far in this part of the lecture. So, in this lecture, I have first described or discussed the petrogenetic implications of the isotopic systems, namely the rubidium strontium system and the samarium neodymium system. So, we have seen how the strontium isotope have evolved through time, and also the neodymium isotopes, and how this evolution has a petrogenetic importance, meaning that if we collect a rock from the nature and measure the strontium and the neodymium isotopic ratios, we can easily find out or can analyze the source of these rocks, whether it is crust or whether it is mantle, or whether there is any mixing between these distinct sources with distinct isotopic composition. Then we moved on to develop some concepts which is required for the radiometric dating, for example, the blocking temperature and the concept of geological ages. And then we moved on to discuss the whole rock ages and the ages of single minerals. For whole rocks, we have discussed two isotopic systems, the rubidium strontium and the samarium neodymium. The different isotopic ratios can be measured directly from the sample and can be also found out from some graphical analysis, and we can solve for the term T, which is actually the age. But we should be very careful about how to interpret the number what we have got from these equations based on the blocking concept of the blocking temperature and what kind of geological ages we are trying to find out. We should treat these numbers very carefully. We should also keep in mind that these numbers or the ages might be discordant from different isotopic systems, and we should look carefully into the different systems and understand them to carefully interpret these ages. Then we moved on to the single dating of the single minerals, which is something different from the ages obtained from the whole rocks. We actually find the concentrations of these isotopes from single minerals. In this section, we discussed about three different three different isotopic systems, the rubidium strontium, samarium neodymium and the uranium lead, and the techniques in these isotopic systems are also very similar to that of the whole rock, but the ages might be different, and again we should be careful about how we interpret these ages, as keeping in mind the blocking temperatures of different minerals with respect to different isotopic systems. Thank you.